We are going to introduce linear functionals, okay, and dual spaces. So before we even talk about what linear functions are, let's recall what linear transformations were, or what was the dimension of the spaces of linear transformations. So suppose V and W be two vector spaces, both over the same field, say F. And let's consider the space of linear transformations from V to W. Assume moreover that dimension V is equal to M, say, and dimension W is equal to N. Okay. So let's denote by LVW the set of all linear transformations from V to W. Okay. Is that a vector space? Linear transformations from V to W, the set of all of them. Is, right? Because you have a linear transformation T, another S, T plus S, you can define just pointwise addition, okay? Or you can also define what is A T plus B T dash for two linear transformations, right? Where A and B both are from F. This has a vector space structure. Now, can you tell me what is the dimension of this? Okay, this was just for linear combination of these things. So now we are talking about the dimension of L V W. The dimension of this? Yes? Yeah? The dimension of this is Mn, right? How? Why? The matrices are? Right. So if you are given a basis of V and a basis of W, then the matrix of the linear transformation T with respect to the basis B of V and D of W would have dimension M cross N. Okay. So whatever matrix of dimension M cross N you choose, that would define a linear transformation from V to W in this manner, given two bases of the fields. Okay. So this is just Mn. Okay. Now consider this space, the linear transformation from V to F. A little less speaking, please, Audrija. F is a vector space over itself, right? And the dimension of F over itself is 1. Okay. So this one is the space of linear transformations from V to F. What should be its dimension? That is N. So this we call as the dual space of V. Okay. This star is not adjoint anymore. For vector spaces, this is, well, there is something very confusing for this notation, you will see, because we have seen earlier that if by this you are denoting adjoints, then A star star would be equal to what? A. And we will see that if you take dual of a dual, you are going to get a vector space which is canonically isomorphic with this. So we'll soon prove that is, it doesn't depend on the choice of the basis. So you need not talk about the choice of basis, but for every vector in V, you can associate a vector in V star star, V dual, V double dual. Okay. So that's why you would write that V double star is equal to V. This equal to just means that they're canonically isomorphic. Okay. There's a natural isomorphism between this and this. We'll come to that soon. Okay, but at least we can define it immediately. So this is the dual space of V, and the elements of this would be called linear functionals. So linear functionals are the simplest kind of linear transformation. Okay, they are mapping V to its base field F. Okay. So for example, if you have R2 Well, can you just, it would be nice if the example comes from you. So can you construct a map from R2 to R? Projection, yes. You have some vector v, you are just projecting it here. Okay. So basically the unit vector in this direction, say 1, 0. So you are just taking the dot product of v with this. Okay. So the map is just v is going to v transpose 1, 0. That's an example of a linear functional from R2 to R. So this is dual space of v, and the elements of it of v star are called linear functionals. Okay. All right. So then this one is the double dual. And what should be its definition? Yes, right. So L of v star to f. Okay, all the linear functionals from the space of linear functionals to f. Okay. All right. So now, given a linear functional, what should be the dimension of its kernel? Kernel, suppose f is an element in v star. Okay. So we are asking about dimension of the kernel of f is what? Yes. Remember, this is just a map from f is a map from v to f, right? Unless f is identically 0, its image will have dimension what? 1, right? So now you can apply, yes, Rank-Knight theorem, right? So dimension of kernel of f plus dimension of image of f is equal to the dimension of v. Okay. Dimension of v. Okay. So if f is not identically 0, then dimension of image of f, then this one is equal to 1, right? All right, because then f is mapping to some non-zero vector of non-zero element of f, and then I mean what I want to say is that if f is not identically 0, then there is some vector which is being mapped to a non-zero element of f. Take any linear multiple of take any scalar multiple of that. So you are getting any scalar multiple of that non-zero element in f. So you will get the entire f. Okay. Thus, if f is not identically 0, its image would be entire f. Okay. And therefore, the kernel will have dimension 1 less than the dimension of v. Okay. So if dimension of v is equal to n, then dimension of kernel of f is equal to n minus 1. Okay. All right. So now, given a vector space, the subspaces of it of dimension n minus 1 will have a name for them. Okay. We'll call it a hyperplane. Okay. hyperplane. What are they? The subspaces of a vector space V of dimension 1 less than the dimension of V. So, a vector space V, say, of dimension n and the subspaces of dimension n minus 1. Is it clear? I mean, what we mean here? Maybe we introduce some more notations here. The subspaces W of a vector space V of dimension n. This makes sense such that dimension of W is equal to n minus 1. All right. So, this is called a hyperplane. Okay. Same way, till now we have defined what is a dual space. At first, we saw the space of linear transformations from V to W. Okay. And if V has dimension m, W has dimension n. So, the linear transformation from V to W has dimension m times n, because it should be the size of the matrices of, m cross n, such that the columns of the matrices are giving all the possible linear combinations of, the columns of the matrices are explaining the image of one basis in terms of the other one. Okay. So, if this has dimension m, the other one has dimension n, it should be just m times n. Okay. So, in particular, this vector space, this is just a set of linear transformation from V to F. It will have dimension n times 1. So, just dimension n. Okay. That is a dual space. That is how we define a dual space of a vector space given vector space V. And similarly, the double dual would be set of all linear transformations from this space to F. F is the field on which the vector space is defined. Okay. And the elements of the dual space will be called linear functionals. Then we came to that thing that if F is a linear functional from V to F, then its kernel should have dimension n minus 1, which is following from the rank 90 theorem, unless F is identically 0. Okay. So, and then we defined a hyperplane to be a subspace of V which has dimension just 1 less than the dimension of the entire space. Now, the question becomes is, well, at first we note that the kernels of non-zero linear functionals are hyperplanes. Then the question is that, is every hyperplane the kernel of some linear functional? So, what is your guess? What is your guess regarding this? Yes, we can do this. Okay. So, I am going to show you how to do this, but before that, let us introduce something called a dual basis. Okay. So, suppose, let V be a vector space of dimension n, and let B equal to V1 Vn be a basis of V. Okay. We define the dual basis by, well, at first let's define it. Maybe we write some linear functions here, if1 dot 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 fn, say, and this we define by this thing, if I Vj equal to delta ij, the Kronecker delta function. That is, it is taking the value 1 if I is equal to j and 0 otherwise. Okay. So note that if you define the, linear map, well, if you give values of the linear functional on the basis elements, you have given its values over the entire vector space, right? So how you are doing this? You are defining fi of Vj to be 1 unless, well, fi of Vj to be 1 if and only if I is equal to j. In every other case, you are defining it to be 0. Okay. So for example, how does the matrix of this linear, well, every linear functional is a linear transformation of the simplest kind, right? So how should its the matrix of this linear transformation look like? Identity? Exactly, all zeros except 1 in the ith position. Because how do we define the matrix of the linear transformation? We defined, suppose T was a linear transformation, then we said that it is TB is equal to BA, and this A is the matrix of the linear transformation, right? Now instead of TB, we'll have if I of B, right? And well, that was, sorry, not that was, excuse me, that was not linear transformation. What we just said, that was a linear operator. But for a linear transformation, we said that TB is equal to DA. D is the basis of the image space. B is not image space, the codomain, I mean. Okay. And B is the basis of the the domain. And then you are writing the images of the basis elements in terms of the new basis there. Now, given the field, what is the natural choice for a basis? 1 or any non-zero element. Okay. So you are going to write TB. Well, now instead of T, we have the linear functional fi. So let's write it here, fi of B, and here for the basis you are choosing just 1 or any non-zero element of f. Okay. So write it as maybe 1 times A. Okay. So basically, this is the image of all the basis elements. This is just 1, right? So this is 1 times, well, 0, 0, etc., etc., except 1, 1 at the ith position, as Sairam mentioned, and zeros again everywhere else. Ith position. Okay. And since it's just multiplied with 1, you can forget about this and just write that this is equal to this. This is your matrix of the linear functional. Okay. That linear functional which we defined as the dual basis. I mean, as the ith element of the dual basis. Okay. All right. So we know that the dimension of this is equal to n, and we have defined, of course, n elements here. Okay. So what we have to show now? They are linearly independent, right? Now, suppose not. Okay. Suppose we have a linear combination of the elements in the dual basis, which is equal to 0. Okay. So let summation Ci fi I running from 1 to n be equal to 0 such that not all Ci's are 0. Okay. Okay. Let's evaluate that thing at Vj and see what is happening. So that will give us, and if this is 0 for, I mean, if such a linear combination is 0, what it means? It's an identically 0 linear functional. That means it will take the value 0 at every vector of V. Okay. So I running from 1 to n, Ci Fi of Vj, say this is equal to 0 for all j. In particular on the basis vector, this should also be 0, right? Now note that what is Fi Vj? Just delta ij, right? Yes. And if you multiply it with this one, then which one survives? Cj, right? So that implies then Cj is equal to 0 for all j, and you are done. Okay, so that's a contradiction because we assume that not all C's are 0. So that implies that indeed B hat forms a basis of V dual. Okay. And now we are in a perfect position to answer this question. So the question was whether every hyperplane is a kernel of some linear functional. Okay. So how should we begin? What is the dimension of the hyperplane? Suppose W is a hyperplane. The dimension of W is n minus 1. So one of it, I mean, if you take a basis of W, that will have n minus 1 elements, right? Let W be a hyperplane of V, and let by the way, we do not denote the dual basis with a hat. Excuse me. We denote this basis also by a star because it's a dual of the basis of a basis of B. So B dual and what? Between a basis or a vector or a matrix, what should you distinguish? Well, if we write A star, that means a adjoint, not the dual of A. If we write V star, that means it's a dual of the vector space V. And what else? If we write a basis and we write V star, that means it's a dual basis. It should be clear from the context. Why, I mean, what meaning this has. And as we mentioned, this is quite confusing because here you have A, and this we are going to show that this is, well, canonically isomorphic with V. That is, we don't have to refer to the basis of V, or, well, we know that the dimension of V dual is n if the dimension of V is n. And vector spaces of the same dimension are isomorphic. Just take a basis of this, send it to the basis of the other one. But this isomorphism doesn't depend on the basis. So for each element of V, we have a natural association with an element in V double dual. Okay. That's why we write equal here. We'll see this soon. Okay, so let W be a hyperplane of V, and let B, say, V1 dot 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 V n minus 1 be a basis of W. Okay. What should we do now? Yes? V1 up to V Yes, we'll extend it to a basis of V. Yes. Right. Yes. So basically, you are taking the, I mean, you are considering the dual basis of the basis you constructed, and considering the last part of it, the last element of the dual basis. That's it. Okay. Yes. I mean, what you just described is that linear functional. Okay. Indeed, that's the right idea. So this is a basis of W. We extend this to a basis, say B tilde, which we define as V1 dot 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 Vn minus 1 and Vn of V. Then you take the dual of this basis, okay, and let B tilde dual, which should be equal to defined by F1 dot 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 Fn, be a basis of V dual. Okay. The claim is that the kernel of Fn is going to be W. Then kernel of Fn, well, at first we know that the kernel of Fn would have dimension n minus 1, right? And also note that Fn by definition takes the value 0 on all these vectors, right? It takes only value 1 at this extension on Vn. Okay. So everywhere else it is 0. That means the kernel already contains W. Okay. And of course, every element in, well, for the other inclusion, how do we proceed? So we are trying to show that this is equal to W. Okay. Now we know that, I mean, every element in W is killed by Fn, right? I mean, does it suffice to say that this and this are equal? Why not? What are the dimensions? W is of dimension n minus 1, and kernel Fn, since F is not identically 0, it is taking value 1 at Vn. Okay. So its kernel should have dimension n minus 1. Their dimensions match, and this is the subset of that. So this should be equal. Okay. Then kernel of Fn is equal to W. So indeed, every hyperplane is a kernel of some linear function. Okay. Okay. Now it's time to define what is an annihilator. So suppose you are given subset S of V, okay, so annihilator of a subspace. Okay. So let S in V be, well, at first a subset. So S in V just a subset, V a subset. Then the annihilator of S is the set of all linear functionals such that f of V is equal to 0 for all V in S. Okay. I note that, I mean, irrespective of whether this is a subspace or not, for every subset, the annihilator, well, we denote it by S0. Okay. So this one is going to be a subspace of V dual, because if f is 0 on this, and if something else, say f dash is 0 on S as well, so you can take any linear combination of f and f dash, and then that is also going to be, I mean, that linear combination is going to be 0 on S. Okay, so this is a subspace of V dual. Okay, all right, and we are going to prove a small theorem soon. That is, so for all subspaces W of V, we have dimension W plus dimension W0, that is the dimension of the annihilator, is equal to the dimension of V. Okay, and the trick is quite similar to what we did there. Okay, so what should we do? We will take a basis of W, yes, and then extend it to a full basis of V. Then consider the dual basis. Then, yes, Manideep? Yes, annihilator of a set is a set of all linear functionals which are taking value 0 on that set. It's annihilating S. Okay, all these linear functionals are annihilating S, right? Okay, so now let's come back to the proof of this. So again, go on. So we have taken a basis of W. We extend it to the entire basis of, I mean, the basis of the entire space V, and then we consider the dual basis. Okay, and then any linear function from the dual basis. Yes, we are looking for a basis of the annihilator. Like here, we were looking for a basis, well, an element which will annihilate this W. This W, so that the W is the kernel of that. Okay, so now we are looking for a set of elements, a set of basis elements of V star, which annihilates this one. And we already have a choice of the basis of V star, V dual. What was that? The dual basis of the extended basis of W. Okay. So what are the natural choices? Right. Yes. Very good. That's the idea. Okay. Yes. That's actually the proof. Okay. So let's do this. Where? Or maybe here. Okay. Actually, this proof itself could be modified. Instead of a hyperplane, now we are having a space, vector space. Okay. So let W be a subspace of V, and let not n-1 but R. Okay. V1 to Vr be a basis of W. Extend B to a basis B tilde, and now it will have elements V1, V2 dot 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 Vr, and then Vr plus 1 dot 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 Vn. Okay. And let now B tilde star, which is F1 to Fn, well, let's also write this as F1 dot 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 Fr, and then Fr plus 1 dot 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 Fn be the dual basis of B tilde. Then we claim that this part is a basis of W0. Okay. Where should we write the claim? Can you use this part of the board, because we require that for something else? This upper part of the board, where we just wrote the definition of annihilator. claim is that um, if r plus 1 if n is a basis of W0. Okay. And the proof of this claim, how should we proceed? Let's take some linear functional which is annihilating W. Okay. So let f, which is a, since this was a dual basis, that f which we are going to take in the annihilator of W, we can take it as a linear combination of these ones. Okay. So let f equal to Ci fi, I running from 1 to n, be inside the annihilator, be an element in the of the annihilator of W. Okay. Now that implies that if you take an element of W, well, take an element yes, take an element from the basis of from the basis of W. Okay, so V1 to Vr, say some Vi which is between V1 to Vr. Okay, if you evaluate that, what will happen? What will happen is given here. Okay, so just see this one, this equation. Okay, that if we evaluate it at Vj, since that is in W annihilator, so we are having that Ci fi of Vj is equal to 0 for all, not for all j, but for all j in 1 dot 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 up to r. Okay. And what does that mean? This is just equal to Cj, right? So that implies Cj is equal to 0 for all j in 1 dot 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 up to r. We have such an expression, right? Let's wipe this part out. Since f is in W0, that implies f of Vj is equal to 0 for all j in 1 dot 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 up to r. Okay. Now f was a linear combination of this. So f of Vj is equal to 0, that would mean that this linear combination is equal to 0. And by definition, f of Vj is delta Ij. That means Cj is equal to 0 whenever you are having Vj here. Okay. Now which Vj's we are considering? The ones with j in 1 to r. And that means all the first coefficients are 0. What will that imply? That f is having this expression with I running from r plus 1 to n, because everything else is equal to 0. Okay. So that is inside the span of f1, sorry, if r plus 1 dot 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 if n. Okay. So that proves this claim, which I found that there. So this claim, this is indeed a basis of this, because these were linearly independent, and then they are spanning W. Okay. All right, and immediately we can write down a corollary, not that of the theorem, but that of the proof. Okay. And the corollary is this one, that every subspace of V of dimension k is the intersection of n minus k hyperplanes. How do we get this? So what are the hyperplanes? The kernels of linear functions, right? these are those linear functionals of which we are talking about. So each of these linear functionals are, they are having some hyperplane as a kernel, and then W is just equal to the intersection of all those. Okay. So thus we have this. Okay. All right. Now, well, we have seen that if we could express linear function in terms of the dual basis, it's quite easy to get the coefficients, right? Let's formalize that in a moment. Oh, sorry. Let this v1 dot 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 vn be a basis of v, and b star, which is equal to v1 star dot 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 vn star, be the dual basis. Okay. Not, excuse me. If one, so let b star as f1 dot 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 fn, excuse me, be the dual basis. Okay. Now we have seen that this an arbitrary linear functional of v dual. So then if in v dual can be expressed as, so then every f, excuse me, every f in v dual can be expressed as, well, what we did earlier. We expressed this, well, we know that every f in v dual can be expressed as a linear combination of this. Okay. But we also know the coefficients. If this is a basis and if it is a dual basis, we also know the coefficients. What are the coefficients? These ones. Well, this is just f of vj, right? F of vj came out to be cj, because f of vj is this linear combination applied to vj, and the only thing that survives is the jth coefficient. Okay. So in such a linear combination, ci is just the evaluation of f at vi. Okay. So this is just summation f of vi fi, I running from 1 to n. Tell me who is stuck with this. Abortho, are you all right with this? You're getting this? I mean, we said that suppose this is, so suppose your f is equal to summation ci fi. Okay. Then note that if you evaluate f at vj, that would just give you cj. We just wrote it down also here. Okay. So since cj is equal to f of vj, you just replace that by f at vi. Okay. That's what we did here. All right. And also, we can do something similar for a linear functional when we are considering, well, suppose this is a basis. What we did here now, we express this in terms of, I mean, the coefficients of the linear functional in terms of the dual basis. Okay. Now, given a basis and given the dual basis, we can also express the elements of the vector space V in terms of the basis where we express the coefficients in terms of the dual basis. Let's see how. It's exactly the same logic, but from the other direction. Okay. and all is depending on the fact that dual basis is defined in such a way that Fi of Vj is delta Ij. Okay. So suppose V is equal to summation Ai Vi I running from 1 to n. The claim is that Ai is equal to what this is going to be Fi of V. Very good. Fi of V, right? And let's check whether that is true. So suppose we have this one, and then Fi of V is going to give you what? Summation I running from 1 to n Ai. Maybe we can change the names. This is a time variable, we change it to j. Okay. So Aj Fi Vj, right? All right, and which one will survive? Only the case when j is equal to I. Everything else will be by Fi. Okay. So this will just give off Ai. So indeed, if you have this basis, I mean, if you have V1 to Vn as your basis, then you can write this as, well, this one as then equal to summation I running from 1 to n Fi of V Vi. Okay. So with the dual basis, thus we can not only write down the coefficients, not only write down the basis elements, but also coefficients in both spaces. Okay. So now comes the last part, that is V and V double dual are canonically isomorphic. So, I am going to show that V is equal to its double dual. Okay. So, that means with each element of V, we are going to associate some element of V double dual without referring to any basis. Okay. So, let V in V. We shall map V to EV, that is evaluation at V of, well, what are these elements again in the dual space? They are maps from the dual to F. In the double dual, it's a map from the dual of V to F, right? So this would be a map from this to F, and so this is the evaluation map. And the definition is rather clear by, I mean, the name is rather, well, what I want to say is that the name defines already the map, because what are the elements here? Linear functionals, right? So EV of the linear functionals are defined as f of V. Just that, quite simple. Okay. Well, we know already that their dimensions match, right? All we have to show then is that this map is, at first, it's a linear transform. I mean, it's indeed a linear map, and then it's, so do we need to show bijection? Because here we already know that dimension V is equal to dimension V dual is equal to dimension V double dual. So we need to show what? Yes. So at first, the first claim is that claim 1. This map, that sends V to EV is linear. Okay. So it's a linear transformation, and then claim 2. What more is left to prove then? It's a linear map from V to V double dual. These are, yes, but you already have some information that their dimensions match. So do you have to show it is both injective and surjective, or just doing one? Only one would suffice, right? Yes. So let's claim that the map is injective. Okay. Yeah, surjectivity would also suffice, but let's prove the maybe the harder looking thing, that is injective. It's not hard actually. So yeah, so if you could show that it's injective, then this definition, since it's an injective map from between two vector spaces which have the same dimension, it would follow that they would be the same. They would be, I mean, this is going to be an isomorphism, right? Because the map is injective. That means the at first, if it's a linear map, that means the image is a subspace of the space V double dual, right? And then if it's injective, that means the kernel is having dimension 0. Okay, so the image has the full dimension, okay, because their dimensions are matching. Okay, so if we prove these two claims, then we are done, because this isomorphism is not referring to any basis of V or V dual. Okay. All right. So at first, suppose you have some AV plus BW, okay, and the evaluation map at this should be equal to what? So this is the claim, the first claim, okay, claim 1, proof of claim 1, okay, and this is A times EV plus B times EW. This we need to show. Okay. So this is, well, this is not yet the proof. This is to show. Okay. And the proof begins from here. So EAV plus BW of some linear functional f is equal to f of AV plus BW, but it's a linear functional, so this will break over, right? AV plus BFW, okay, and then that's the claim, right? AEV of f plus BEW of f, that is AEV plus BEW of f. So indeed, this is equal to this one, because it is matching over every element of V12. Okay. The first claim is done. Now about the next one, that it is injective. Suppose not. Suppose there exists some V in V such that EV of f is equal to 0 for all f in V dual. Okay. And this V in V not equal to 0, of course, because if it is 0, it's a linear map. 0 is sent to 0 by default, right? So this V is not equal to 0 such that this is equal to 0 for all f in V12. So please complete the proof. How should proceed? You have enough things to complete this proof already. Yes, that means f of v is equal to 0 for all f in v dual. Yes. What are FIs? We are not referring to the basis. At first you have to construct a basis. Which basis? Basis of the, well, that FIs were considered, I mean, we given a basis of V, we constructed a dual basis. Indeed, we have to go through the dual basis, but at first you need a basis of V. Which basis you are talking about now? Which basis? I mean, where do you start? It's an arbitrary basis? No, it's not, because you required that this is not equal to 0. So, yes? Right? Yes. So you have to construct a basis of which, well, you please remind me what does the, I mean, how we define the dual basis. So suppose we are given a basis. What does the dual basis do? It takes all the other basis elements to 0 except 1. Okay. So use that fact. Then, I mean, what you are doing, please, I mean, that's the idea. Yes. Extend V to a full basis of, right? So take the dual basis then. I understood. Yeah, what you want to say. So take a basis of V, which is constructed out of, I mean, which is just an extended part of this. So all these ideas, what you came up one after another, was all correct. But at first, so indeed we are using the dual basis, and the fact that the dual basis doesn't send, I mean, all the elements of the dual basis cannot send the entire basis, the other basis, the original basis to 0. So there should be an element in the original basis which is not sent to 0. Okay. So at first you have to construct a basis of the original space with V as a basis element. Okay. In other words, you start with V and extend it to a full basis. Okay. V2 dot 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 Vn. Okay. A full basis of V. Okay. Take the dual basis of that. Yes. If we construct a basis without V, then how do we proceed? Of, right? All the FIV would be, okay, let's, indeed, yes. So maybe we can try later. I mean, we are just trying out what you mentioned, but at first let's finish this argument and then we are going with that. Okay. So let B be a basis of V, okay, which we got starting with V as our first element, and that we can do because V is not equal to 0. Okay. Let this be the dual basis. Okay. So F1 dot 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 Fn of this. Okay. Let this be, well, it's understood. Dual is just dual basis of that. Okay. Yes. Exactly. Then F1 of V is not equal to 0. So that gives a contradiction. Okay. And that finishes the proof. Okay. Now let's see the other way that you were saying. That is, you want to start. Yeah. Okay. So at first, since V is not equal to 0, you can start with it and complete a full basis of V, right? This up to this, you are with me? From V. So take V, take the what? Well, this V, the span of that, what is the dimension of that? Dimension of? So V is some non-zero vector in V. Okay. What is the dimension of the span of that? How many linearly independent vector can belong to the span of a single vector? In? Are you sure? So you want to say that in R2 you can get to linearly independent vectors on the line? You cannot, right? So how many at most? 1. Dimension of the span of a single vector is 1, because every other vector is a linear multiple of this, right? So this has, the span of that has dimension 1, and that means you have this as a basis, as a basis of the subspace, which is spanned by this, and you can of course extend this to a full basis of V. Okay, if V is of dimension 1, it just stops here. Okay. If it is of dimension 2, there should be some linearly independent vector which you can choose and complete the basis. If it is not of dimension 2, you can extend it further. Okay. So suppose it is we want V2 to Vn, then we take the dual basis, F1 to Fn, and then you know that the dual basis takes the corresponding elements to 1 and everything else to 0. So in particular, F1 of V is equal to 1, which is not equal to 0, and that contradicts this thing. Okay, that F of V is equal to 0. So that means if V is some non-zero element of the vector space, then evaluation at that cannot take every linear functional to 0. There is some linear function which is non-zero there. So in other words, we have already proved that this map is injective. Okay. That completes the proof of this, that V and V dual are canonically isomorphic. Okay. That V goes to EV is canonical isomorphism. Okay. Now let's come back to your idea. Okay. So you said that instead of starting with the base of the first element as V, you take any basis of V. Okay. So let this be now an arbitrary basis of V, and let this be the dual basis. Okay. So we don't have this condition yet, but we can write V. So if this is an arbitrary basis of V, that implies that V is equal to linear combination of these ones, right? Summation Fi V and Vi, right? I running from 1 to n. Yes? Then? Wonderful. Yes, sure. So if Fi V is equal to 0 for all I, that would imply V is equal to 0 for if V is just equal to 0, right? Because this is a linear combination, every coefficient is 0, so this is 0. In either way, we got the proof of the second claim, and therefore this, the equality, not equality, the canonical isomorphism between V and V double dot is established. All right, with that we must end this class. Wish you all the best for the exam.